So now let's talk about the electric field. So if you recall the principle of superposition, the principle of superposition says that the total force on a charge from a set of source charges on your test charge is the sum of all of these forces together. So you can write that as 1 over 4 pi epsilon naught, say q1 over curly r1 squared r1 hat times q, and so on. And you notice that you can write this as a sum rather than writing out each individual term. So you can write this as the sum from I equal to 1 to n, where n is the number of charges I have, 1 over 4 pi epsilon naught, q sub I, big Q, over curly I r sub I squared, r sub I hat. And so the r sub I is the curly r for each of the individual charges. Now big Q doesn't depend on I, the charges, and so I can pull that out of the sum. And so when I pull it out of the sum, then I have something that looks like this. The total force is big Q times this quantity, and this total quantity, Qi Ri hat over curly I Ri squared, is actually independent of the test charge, big Q. Since it's independent of the test charge and only depends on the source charges, we define this as some new object. We call this the electric field E. And the electric field E actually, since it has a curly r hat, is a vector, so it's a direction. So we say the electric field, just restating this, the electric field E for a set of point charges, it depends on the position that you're interested in the electric field at, which is r vector. So 1 over 4 pi epsilon naught, the sum from I equal to 1 to n, q sub I for curly r sub I squared, r sub I hat. And we still call this Coulomb's law, even though it's not a force, it's really Coulomb's law for the electric field for a set of point charges. Okay, so this is true for point charges. You just add up the electric fields together, vectorally. But what if you have actually a lot of point charges? So usually you don't just have a single charge hanging around, you have a smearing of charge, or you have a total object which is charged. So what we want to do now is consider what happens when you have a lot of point charges, and you change that into some kind of smooth charge distribution, where charge is smeared out over an entire surface. So this might be like if you put charge on a conductor, the charge will smear out over the entire conductor, rather than being localized to just one point. So the change that we need to make is, for point charges, we had this electric field, which involved the individual charges of the individual points. And so now we're going to write the electric field in a new way. For smooth charge distribution, there's still the 1 over 4 pi epsilon naught, but now it's going to be the integral of dq over curly r squared, curly r hat. So we turn the sum into an integral, which makes sense, and the individual charges turns into little dq's, which are small amounts of charges. So essentially we're still doing Coulomb's law for point charges, just doing it for lots of tiny little charges, dq. You can imagine taking a little chunk, dq, in your charge distribution. So there's three main types of charge distributions, smooth charge distributions. One type is the line charge. And so for this, consider a line, and then I'm going to draw in the coordinate system here. And on this line charge, there is some amount of charge dq. And we're interested in the electric field due to this little dq at some point P up here. And so there's some r prime vector, which points to the charge, r vector, which points to the point P, and then a curly r vector, which points from that little bit of charge to the point P. Similarly, you can also have a surface of charge instead of a line of charge. And so now there's some little bit of charge on your surface. And so we're interested in the electric field created by this little bit of charge here at some position r prime. And we're interested in the electric field at some point P, which is at some vector r. And so there's a curly r associated with each of these little dq's. And finally, there's also a volume charge. So you could have a charge in a full three-dimensional volume of space. And so Here we have some charge all spread out, and there's some little cube of charge, little dq cube of charge at some position r prime, and it creates an electric field at some point P, which is at some position r. And so there's a curly r vector associated with each of these little dq's. So line charges are characterized by something called lambda, the charge per unit length. And so then this little bit of charge dq is lambda times dl prime, where dl prime is some small amount of length. In general, we're going to use prime for distances on the charge distribution. The surface charge is characterized by the sigma, the charge per unit area, and then dq is sigma times a small amount of area, that small amount of area on the surface. And finally, for a volume charges are characterized by the quantity rho, the charge per unit volume, and a little bit of charge dq is then equal to rho times the small amount of volume. And so this is how we're going to relate our charge distributions and our little dq's into integrals over coordinates. So then we can write the electric field for a line charge is 1 over 4 pi epsilon naught, lambda, which depends on r prime, r hat, curly r hat over curly r squared, and you're integrating over dl prime, the length of the line. The surface charge is something similar. You have an integral sigma, curly r hat, over curly r squared, dA prime, so you're integrating over the total area. And then for the volume charge, you're going to integrate over then the volume. And so you have an integral over rho, curly r hat, over curly r squared, d tau prime. So we've just replaced dq with the appropriate quantity for each of these from our more general form. So notice that a line integral gives you, or a line charge gives you a single integral. A surface charge gives you a double integral. And then, of course, a volume charge gives you a triple integral. And so that's one way that these all are going to be different and the types of integrals that you have to do.